In the last lecture, we described towed streamer seismics, including the notion of seismic events. We will now describe broadband seismics, that is, ways of widening the spectrum of seismic data. In seismology, broadband is a characteristic of data with a wider band of frequencies compared to data associated with conventional seismic exploration and production. In the marine towed streamer, the data have a usable bandwidth, typically from around 8 Hz to 80 Hz, whereas broadband seismic systems can produce data with usable frequencies from as low as 2 Hz to as high as 250 Hz. The additional low and high frequencies contained in the broadband seismics allow us to produce images of the subsurface, which readily reveal depositional models, something that is not generally possible with conventional seismics. Two of the major factors limiting the data spectra to between 8 and 80 Hz in conventional seismic systems are 1, the ghost effect, and 2, swell noise. The other major factor is that propagating waves attenuate with time due to various energy loss mechanisms that we will discuss in future lectures. The broadband approach here consists of designing the acquisition systems so that we can record data without ghost and swell noise, or in such a way that the removal of swell noise and ghosts become feasible at preferably the early stage of the seismic data processing flow. Our first objective is to describe how the effect of ghost affects seismic frequency bandwidth. The second objective is to describe some broadband towed streamer acquisitions. This is the plan we will follow to describe broadband seismics, beginning with the ghost effect. We start by considering this very simple model to describe the ghost effect on seismic bandwidth. Along with this model, we show the impulse response with ghost. Our discussion in this section will be limited to the case in which the source and receiver distance is 0. That is, 0 offset. We have a combination of 2 impulses, the initial downgoing signal and a second impulse, ghost impulse, of amplitude positive R0, where R0 is the effective reflection coefficient at the sea surface. For a free surface, R0 equals -1. The initial downgoing impulse is a unit impulse at t equals 0, designated delta t. The ghost impulse in this simple case is delayed, inverted, and modified in amplitude with respect to the direct impulse and is given by R0 delta t minus tau. The impulse response of the ghost source distortion filter, HT, is then the sum of these 2 impulses, delta t and R0 delta t minus tau. OS indicates the ghosted trace is produced by the additional filtering action of the ghost distortion operator, HT. We can consider the ghost as an additional time domain filter in the reflection path. The top figure shows the non-ghosting case. Here the source signature ST is generated, and it alone enters the downgoing path, for this case, HT equals delta t. In the bottom figure, the source signature ST is generated at the shot, and after passing through the filter HT, both ST and R0 ST minus tau enter the primary reflection path. Let's look at the frequency bandwidth of a signal containing ghost for the simple model in which the signal containing the source ghost can be described as the convolution of the source signature ST, used to generate data, and the source ghost distortion in the water, HT. We define the delay, tau s, as the ratio of twice the source depth with respect to the sea surface over the velocity of the water. We here have two signals on top and the amplitude spectra below. We selected to work with the zero-phase source signature for ST. The amplitude spectrum of this source is given in blue. The signal containing the source ghost is OST, and its amplitude spectrum is shown in black for source depth equals 6 meters. We can see that the spectrum of the signal containing the source ghost is narrower than the signal without the ghost. Note that the spectrum of the signal containing the source ghost is the black curve. The spectrum of the signal without the ghost is the blue curve. The ghost distortion affects seismic data twice on the source side as well as on the receiver side. We can describe the receiver ghost signal as a convolution of the source signature with a combination of the source and receiver ghost distortion. Basically, we have the output signal being a convolution of the source with the source ghost distortion plus a combination of the source and receiver ghost distortion. The signal OT contains source ghost and receiver ghost. Its amplitude spectrum, shown in red for receiver depth, equals 9 meters. We can see that the amplitude spectrum of the signal containing both source ghost and receiver ghost distortions is even narrower than the signal without ghost. The process of going from signals with ghost to signals without ghost is generally known as signal broadening, or a seismic broadband. In practice, we record the signal with ghosts, and we seek to recover the signal without ghosts through data processing. Modern seismic acquisition systems, in which pressure data are recorded, along with the particle velocity, are designed to facilitate this signal broadening process. Again, we here have two signals on top and the amplitude spectra below. The signal containing the source and receiver ghosts with the source depth equal to 6 meters and the receiver depth equal to 12 meters. We can see that as we increase the source and or receiver depth, not only do we narrow the signal bandwidth, but we also introduce notches in the signal spectrum. Now source depth equals 6 meters and receiver depth equals 45 meters. The point in these latest figures is to reiterate the fact that as we increase the source and or receiver depth, not only do we narrow the signal bandwidth, but we also introduce notches in the signal spectrum. In summary, the signal containing ghost is broadened in time, and therefore the apparent bandwidth in the frequency domain is significantly reduced compared to that of the source signature used to generate data. This reduction in bandwidth occurs on the low frequency side as well as on the high frequency side. Lowering the receiver depth to 12 meters or greater is often desirable in order to avoid the effects of the sea surface roughnesses, and it also adds notches in the amplitude spectrum. Restoring the seismic signal to a bandwidth close to that of the signal without ghosts is the challenge of broadband seismic data acquisition and processing. We have seen some notches in the spectra of data with ghosts. Let's elaborate a little more on the notion of notches. Again, a zero-offset seismic trace containing only direct wave and source ghost can be approximated as the convolution of the source signature with the ghost distortion. Ideally, the simplest way to reduce the ghost effect is to shoot either at the surface or at a shallow depth, so that the direct source pulse and the ghost overlap. We here illustrate the net downgoing waveform for both a large and a small delay. When tau is large, two separate pulses enter the primary path. Consequently, each reflector in the subsurface gives rise to two events. If tau is small, the initial downgoing pulse is followed so closely by the ghost pulse that overlap occurs. And for visual purposes, each reflector in the subsurface gives rise to only one event. In the third case, ghosting can effectively be treated as a part of the seismic source signature. Notice that ghosting can be further analyzed by taking the Fourier transform of the ghost distortion HT. That is, H omega equals 1 plus R0 times the exponential of minus I omega tau. If R0 is minus 1, the amplitude spectrum is given by H omega equals 2 times absolute value of sine omega tau over 2. Basically, we have just made a Fourier transform of the two delta functions of the ghost distortion. The amplitude spectrum has notches, which are the frequencies at which the amplitude spectrum is minima. Since minima occurs at f equals 1 over tau, 2 over tau, 3 over tau, and so on, the ghost delay times tau, and thus the shot depth, can be determined since the water velocity is known. Now it's time for a quiz. Determine the frequency at which the first notch occurs when the source depth is 6 meters, 12 meters, and 30 meters. Here's your answer. The first notch is equal to the velocity of water over the source depth times 2. For source depth equals 6 meters, we have the first notch at 125 Hertz. For most of the seismic frequency bandwidth, we don't have notches. For source depth equals 12 meters, we have the first notch at 62.5 Hertz. For source depth equals 30 meters, we have the first notch at 25 Hertz. Let's now talk about deghosting, based on the very simple model of ghost effect we have used so far. Let's consider the ghost response measured on hydrophones and geophones. A hydrophone is a recording device which measures wave field pressure. It is insensitive to the direction of the wave, and therefore detects no difference between an upgoing compression and a downgoing compression. A geophone measures the velocity of a wave's displacement proportional to the pressure derivative. It detects a difference in sign between an upgoing compression and a downgoing compression. Thus, the pressure measurement on the hydrophone is not dependent on the direction in which the wave is traveling, whereas the particle velocity measured on the geophone is dependent on the direction. For a hydrophone measuring pressure, the impulse arriving at the hydrophone from below produces a positive initial output. When this pulse is reflected at the free surface, then the reflected pulse is negative, since R0 equals minus 1. Therefore, the impulse of the ghost distortion corresponding to the hydrophone's pressure measurement is HPT equals delta T minus delta T minus tau. Please pay attention to the minus signs before the ghost distortion. We will come back to this. For a geophone, which measures the vertical component of the particle velocity, an impulse arriving at the receiver from below produces an initial output that is positive by definition. The reflected signal will have negative polarity, but the geophone will measure the negative of the downgoing signal, which has a positive sign. Thus, the impulse of the receiver ghost distortion corresponding to the geophone's velocity measurement is HVT equals delta t plus delta t minus tau. Notice that we now have plus in front of the ghost distortion. Finally, since the overall system response is the sum of the individual responses, receiver ghost can be suppressed by summing the seismic traces recorded on hydrophones and geophones. Thus, a simultaneous recording of pressure and particle velocity can aid in the process of attenuating receiver ghosts, which is known as receiver-side deghosting, as illustrated above. Here are illustrations of the ghost distortions in the frequency domain. The first picture in orange shows the amplitude spectrum of the hydrophone ghost distortion. The second figure in blue shows the amplitude spectrum of the geophone ghost distortion. Notice that the third picture on the bottom is a superposition of the spectra of the hydrophone ghost distortion and the geophone ghost distortion. We can see that the sum of these two distortions allow us to flatten the spectrum of the data. In other words, we end up with the spectra of the delta function and therefore no ghost. Let's now talk about the deghosting of multiple offset data. As we described earlier, seismic reflection events can be grouped into primaries, internal multiples, free surface multiples, receiver ghosts, and source ghosts. Alternatively, we can group these events into primaries, source ghost of primaries, receiver ghost of primaries, free surface multiples, source ghost of free surface multiples, receiver ghost of free surface multiples, internal multiples, source ghost of internal multiples, and receiver ghost of internal multiples. The keys in conventional seismic processing include 1. Removing free surface multiples, internal multiples, and their ghosts from the data, and leaving primaries and ghosts of primaries only. And then 2. Locating the scattering points and reflectors inside the medium, using primaries and ghosts of primaries. In other words, in the last step of conventional seismic processing, ghosts of primaries are treated as components of primaries. In contrast, the processing of broadband data includes 1. The removal of source and receiver ghosts from the data, leaving only primaries, free surface multiples, and internal multiples. 2. Removing free surface multiples and internal multiples, leaving only primaries. And then 3. Locating the scattering points and reflectors inside the medium using primaries only. The first step in this process is known as deghosting, and the second step is a demultiple. So the key difference between conventional processing and broadband processing is that broadband processing includes a deghosting step, but the conventional processing does not. So the removal of ghosts from seismic data is central to the broadband processing. Let's repeat this due to its importance. The removal of ghosts from seismic data is central to the broadband processing. To add more concreteness to our description of broadband data, let's look at a specific example of data with and without ghosts. This figure illustrates the difference between data with and without ghosts. That is, between conventional processing and broadband processing for a simple 1D model. The source depth in this example is 6 meters, and the receiver depth is 15 meters. A has data with source and receiver ghosts. The receiver is 15 meters, and the source depth is 6 meters. We have removed direct arrivals. The offsets vary from 0 meters to 2,000 meters. B has the same data with source ghosts but without receiver ghosts. C has the same data without source ghosts or receiver ghosts. Because ghosts of primaries and multiples arrive at almost the same time as primaries and multiples, we can see that the data corresponding to conventional seismics and those corresponding to broadband seismics are quite similar in terms of events. However, the apparent source signature in conventional data, that is, data with ghosts, is broadened in time, and therefore the apparent bandwidth in the frequency is significantly reduced compared to that of the source signature used to generate data. Here are the frequency spectra of the data shown in the previous slide. Notice that data without source ghosts and receiver ghosts have more low and high frequencies than data with ghosts. Again, because ghosts of primaries and multiples arrive at almost the same time as primaries and multiples, the apparent source signature in conventional data, that is, data with ghosts, is broadened in time, and therefore the apparent bandwidth in the frequency is significantly reduced compared to that of the source signature used to develop data. This reduction in bandwidth occurs on the low frequency sides, as well as on the high frequency end. Notice that the data containing source ghosts only, that is, no receiver ghosts, contain 1 notch, whereas the data containing receiver ghosts contain 2 notches because of the receiver depth. The effect of these ghosts is that both low and high frequency information is significantly reduced, and therefore seismic imaging cannot take advantage of all seismic frequencies. Likewise, at each receiver location along a streamer, a time-delayed reflection from the sea surface, which is the receiver ghost, continuously interferes with the seismic wave field, which is scattered directly from the Earth to the streamer. The nature of these interferences varies with the depth of the source, for the source ghost, or the depth of the streamer, for the receiver ghost. In regards to the receiver ghost for any given streamer depth, the amplitude of the data at certain frequencies will be completely canceled at the recording sensor, that are notches, and the amplitude of other frequencies will in fact be doubled, that are peak amplitudes. Overall, the peak frequencies move toward lower values as streamer depths increase, and vice versa. The challenge of broadband acquisition is to collect data in such a way that all source ghost and receiver ghost effects would be removed during seismic data processing. So while the lowering of streamers to a depth of 10 meters or more is useful in preventing swell noise, this lowering adds notches to the reduced apparent bandwidth. The notches must also be eliminated from the bandwidth. So restoring the seismic data to a bandwidth close to that of the data without ghost of primaries and ghost of multiples is the challenge of broadband acquisition and processing systems. Let's emphasize that broadband seismics are more than a notch filtering process. For example, we can broaden the data bandwidth by going from data with source ghosts to data without source ghosts, even when the spectrum of the data with source ghosts does not have notches. as is typical for data spectra limited to 100 Hz. The goal of broadband data acquisition is to redesign the acquisition system so that we can record data without ghost and swell noise in such a way that the removal of swell noise and ghost becomes feasible at preferably the early stage of the seismic data processing flow. The acquisition of pressure data, that is, hydrophone data, along with the particle velocity, that is, multi-component geophone data, allows us to effectively perform receiver deghosting at the earliest stage of processing. Similarly, simultaneous data acquisition with monopole and dipole sources allows us to perform source deghosting. We now describe the typical examples of this approach. We will start with the measurement of the particle velocity in towed streamer. Measurements of the particle velocity in towed streamer acquisition come down to sensing particle motions in the water column, usually in addition to sensing the pressure. There are two questions here. Number one, why would one like to measure the particle velocity in the water column? And two, how do we measure the particle velocity in the water? In fact, if a geophone which can measure the vertical component of the particle velocity were employed, an impulse arriving at the receiver from below produces an initial output that can be defined as positive. When this pulse is reflected at the free surface, the boundary conditions show that the reflected pulse is also measured as positive. If pressure receivers are employed, an initial upgoing compressional signal will produce an output that we define as positive, and the measured reflected signal will have negative polarity. So going back to our first question, why would one like to measure the particle velocity in the water column? Ghost essentially can be suppressed by summing the seismic trace recorded by the hydrophone and the seismic trace recorded by the geophone. Thus, a simultaneous recording of pressure and particle velocity can aid in the deghosting process, that is, in the process of attenuating the ghost of primaries and multiples. Our second question raised was, how do we measure the particle velocity in the water? Remember the Newton's equation of motion. Force equals mass times acceleration for each particle at a given time. In the water, we have force over volume equals mass over volume times acceleration, or particle acceleration equal to minus the gradient of pressure times the specific volume. Remember that the specific volume is the inverse of density. Vk is the kadiot component of the particle velocity. P is the pressure, and rho is the density of water. The index K here takes the values 1, 2, and 3. Although only volumetric deformation occurs in the water, we are still indirectly able to measure the displacement of particle velocity by using the Newton law of motion. In other words, the Newton's equation of motion in the water provides a way of measuring the particle velocity in the water. This relationship allows us to determine the components of the particle velocity from the gradient of pressure. Some of the measurements of the components of particles in seawater are based on this relationship. Here we focus on the measurement of the vertical component of the particle velocity as an example. One way of performing the measurement of the vertical component of the particle velocity in practice, for example, is to use dual streamers as depicted here. What we have here is a cross-sectional view with 7 shallow streamers and 3 deep streamers. This technique is also known as over-under or dual streamers. the vertical separation between streamers must be small and constant at all offsets. In previous over-under solutions, all the streamers were shallow. In the Craw et al. Solution, there are shallow towed streamers together with a smaller number of deeper streamers, as described here. The shallow streamers have the same coverage as conventional towed streamers, whereas the sensors in deep streamers are sparse. The basic idea is that shallow streamers will give an optimal response from 8 Hz to 80 Hz, and the deep streamer will give low frequencies, including frequencies as low as 2 Hz. The two data sets are then combined in the spectral domain to provide deghosted data with a broadened spectrum. Here are amplitude spectra comparisons of a shallow survey, a deep survey, and the combined over-under data. Notice the significant difference in low-frequency energy between the shallow survey, over, and the deep survey, under. The deep streamer has more low frequencies, but also more notches. An alternative solution to over-under acquisition is measurement of the vertical component of the particle velocity by using solid streamers instead of standard gel-filled streamers. In this case, the geophones are directly placed in the solid. Hence, this measurement of the particle velocity is totally independent of the pressure measurement because it is not based on the Newton's equation of motion. Furthermore, the Carlson et al. Solution avoids the challenging issue of towing two streamers associated with over-under acquisition. However, their solution requires a redesign of the streamers. Note that the over-under acquisition is designed to provide only the vertical component of the particle velocity. However, the idea of directly measuring the particle velocity is valid for the vertical component of the particle velocity as well as the horizontal components, although the current implementation is limited to the vertical components of the particle velocity. We have already pointed out several times that the vertical component of the starting from the beginning of that slide, slide 44. We have already pointed out several times that the vertical component of the particle velocity can be recorded or computed by recording the pressure with two streamers at two depths. We here discuss an alternative solution based on source dipole and reciprocity. The combination of the particle velocity and the pressure allows us to attenuate receiver ghosts by working in the shot-gather domain. We can also use two sources to simulate a vertical force, that is, dipole source, along with the monopole. In this figure, we have the snapshots of a pressure response generated by a monopole source, and vertical dipole, and also a horizontal dipole. Notice how the dipole responses are similar to the particle velocity responses of monopole sources described in lectures on elastic wave propagation. By using the reciprocity relationship, the combination of monopole-generated receiver gathers and dipole-generated receiver gathers allows us to attenuate source ghosts from the data. In summary, one solution of getting the components of the particle velocity in towed streamer data is to record these data components. One alternative technique to obtain the vertical pressure gradient is to introduce data recording with dual streamers, where the pressure field is recorded on hydrophones in streamers at two different depth levels. To avoid complex towing of a dual vertical streamer, one may introduce an acquisition technique with dual sources towed at different depths in front of the seismic streamer. The reciprocity principle shows that the vertical component of particle velocity can be obtained as pressure recording from a source of vertical force. Let's conclude by talking about slanted towed streamers. That is, we design the streamer in such a way that the receiver depth is a variable. This figure shows an example of a slant streamer. The novel ideal here is that the receiver depths along the streamer vary with receiver positions in the streamer. An inherently variable ghost from receiver to receiver are exploited in the stacking process, which is a component of the seismic imaging process, as described by C.G.G. Veritas, to produce imaging results without receiver ghosts. Typically, we have a depth of 7 meters for the nearest receivers to the shot point, and 30 meters to 60 meters for the receivers at the far end of the streamer. The shape of the streamer in the water is almost parabolic, and only the pressure is recorded in the current implementation. Here is an illustration of the data resulting from the slant streamer for a simple 1D model. With this configuration, the receiver ghost notch varies along the cable. And again, this variation of notches can be exploited to produce data without ghosts. Now it's time for a quiz. As described several times, we can group the events in seismic data into the following. 1. Primaries and multiples only. 2. Primaries, multiples, ghosts of primaries, and ghosts of multiples. 3. Primaries only. 4. Primaries and source and receiver ghosts of primaries. 5. Primaries, multiples, source ghosts of primaries, and source ghosts of multiples. 6. Primaries and source ghosts of primaries. 7. Primaries, multiples, receiver ghosts of primaries, and receiver ghosts of multiples. 8. Primary and receiver ghosts of primaries. Here the word primaries includes primaries and internal multiples, and the word multiples includes free surface multiples only. The next 2 slides show some of these groups over the same geological model. The source depth is 5 meters, and the receiver depth is 5 meters. Identify the groups displayed in these slides.
Remember, there is a large selection of iMode education lectures, which can further enhance your knowledge of wave propagation, elasticity, electromagnetism, wave field sampling, wave field decomposition, and imaging. Thank you for listening to this iMode education lecture.